This presentation, titled Digital Twin Applications in Planning, Tools and Practices, is designed to take you under the hood of the technology. We are not just going to look at pretty 3D pictures, we are going to explore the rigorous system architecture, the complex data layers, and the simulation technologies that power these systems. We will examine the entire ecosystem, from the sensors on the street that capture data to the algorithms that process it. By the end of this lecture, you will understand the mechanics of how we turn a static 3D model into a dynamic, living planning instrument. Let's look at our roadmap for today's session. We have structured this lecture to build your technical knowledge layer by layer. First, we will establish the theoretical foundation by examining the system architecture and the 5-dimensional model. We need to understand that a digital twin is a system of systems, not just a single file. Next, we will systematically break down the planning tech stack into 3 critical layers. We'll start with Layer 1, data capture, moving up to Layer 2, integration, and finally Layer 3, visualization. Following the stack, we will tackle the most critical technical concept for planners, data standards. We'll discuss why CityGML and ADA are essential for analysis. Once we have the data structure, we will see it in action with specific simulation tools for wind and flood analysis. Finally, we will wrap up with best practices for implementation and decision support. Before we dive into the technical details, let's clarify our learning goals. What specifically should you take away from this module? First, and most importantly, you should be able to define the digital twin architecture. I want you to move beyond the simplistic idea of a 3D model and understand the 5 dimensions, including connections and services, that make a twin alive. Second, you will learn to distinguish between a dumb geometric mesh, which looks good visually but holds no data, and a smart semantic model like CityGML, which can answer complex planning questions. Third, we want you to be able to identify the right tool for the right job, knowing exactly when to use CFD for wind analysis or hydrological modeling for floods. And finally, you will be equipped to evaluate the entire data workflow, understanding the challenges of transforming raw sensor data into actionable decisions. Let's start with the theory. A very common misconception in our field is treating a digital twin as just a high-quality 3D model. But academically and practically, that is incorrect. As defined by Tao et al. And visualized here in the figure from Steindl's research, a mature digital twin is a 5-dimensional system. It starts with the physical entity, the real buildings and roads. Then, we have the virtual entity, the digital mirror. But these are just 2 dimensions. To make it a twin, we need the other 3, data, connections, and services. The connections are the IoT sensors and networks that flow data in real time. The services are the simulations we run. The key insight here is simple: if you disconnect the data flow or remove the services, the system dies. It stops being a digital twin and reverts to being just a static digital model. Now, let's look at the tools themselves. We can visualize the technology ecosystem as a 3-layered stack, as shown in the GDTA model by Steindl et al. At the foundation, we have Layer 1, data capture. Think of this as the sensors of the city, the eyes and ears that collect raw information. In the middle, we have Layer 2, processing and integration. This is the brain. Here, we take raw data and make sense of it, fusing broad GIS maps with detailed BIM building models using ETL tools. Finally, at the top, we have Layer 3, visualization. This is the interface, what you, the planner, actually see. Whether it's a dashboard or a VR headset, this layer presents the insights. A successful digital twin requires a seamless flow of data up through the stack, from the street sensor all the way to your screen. Let's zoom in on Layer 1. How do we actually digitize physical reality? We primarily use a hybrid approach. First, we use LiDAR, which stands for light detection and ranging. This creates a point cloud, millions of laser points that give us perfect geometric precision. If you need to measure the exact height of a building, you need LiDAR. However, LiDAR points don't look very real to the human eye. So, we combine it with photogrammetry. This technique stitches together thousands of aerial photos to create a reality mesh with realistic textures and colors. This is crucial for public engagement. Finally, we add IoT sensors. While LiDAR and photos capture the space, IoT sensors capture the time. They act as the pulse of the twin, feeding in real-time data on traffic, noise, and air quality, transforming a static map into a dynamic system. Moving up to layer 2, we encounter the biggest technical headache in digital twinning, the interoperability challenge. As planners, we live in two different data worlds. On one hand, we have BIM. It is microscale, dealing with high detail like interiors, typically in IFC format. On the other hand, we have GIS, which is macro scale, dealing with city networks and terrain in shapefiles. The problem is these formats don't speak the same language. As highlighted by Nordo et al., this leads to data loss. To solve this, we use ETL tools: extract, transform, load. These tools act as translators, harmonizing the dataset so that the detailed BIM building fits perfectly into the broad GIS city map. Within Layer 2, we also face the concept of semantic modeling. This is the difference between a pretty picture and a smart tool. In a standard 3D mesh, like you see in video games, a building is just a collection of triangles. It looks like a wall to you, but to the computer, it's just geometry. It doesn't know what it is. In a semantic model, specifically using the CityGML standard, the computer possesses object intelligence. It knows that this surface is a roof, that surface is a wall, and the volume inside is a room. Why does this matter? Because it allows us to query the city like a database. You can ask the digital twin, select all south-facing roofs larger than 50 square meters for solar panel installation. You simply cannot do that with a standard, non-semantic 3D model. Semantic modeling breathes life into a digital replica, transforming static 3D models into a massive spatial database that understands exactly what each component is and how it functions. CityGML is powerful, but sometimes it doesn't have enough fields for specific planning needs. This is where ADA, or Application Domain Extension, comes in. ADA is a feature that allows us to inject non-visual, administrative data directly into the 3D geometry of the twin. As shown in this figure from Aguduro et al., the ADA works by attaching specific data modules, like energy demand or occupancy, directly to the building objects. Imagine clicking on a 3D building and seeing not just its height, but its zoning category or floor area ratio, FAR. By using ADAs, we bridge the gap between the physical reality and the legal reality, enabling features like automated compliance checking. Another critical decision in setting up a digital twin is managing the level of detail, or LOD. We classify models from LOD 0, which is just a 2D footprint, up to LOD 4, which includes full interior details like furniture. A common mistake cities make is trying to model everything at LOD 4. This is incredibly expensive and creates files so heavy they crash computers. For most urban planning tasks, LOD 2 is considered the sweet spot. LOD 2 gives us the simplified building mass and the roof structure. This is exactly enough detail to calculate shadow analysis, solar potential, and wind flow, without the unnecessary burden of modeling every single window frame or door handle. Smart planning means choosing the most efficient LOD for the task at hand. This is the interface where the human meets the data. All the complex math we just discussed needs to be translated into something understandable. We are increasingly borrowing tools from the video game industry, like Unreal Engine, to create immersive, photorealistic experiences. This is vital for public engagement. Instead of showing citizens a 2D blueprint they can't understand, we let them walk through the future park in VR. For mayors and city managers, we use analytical dashboards. These strip away the raw data and present clear key performance indicators, KPIs, allowing for rapid, evidence-based decision-making. This completes our tech stack journey. Now that the system is built, let's run applications. One of the most vital tools for high-density urban planning is CFD, or computational fluid dynamics. As cities grow taller, buildings create urban canyons that can drastically alter wind patterns. Using CFD within the digital twin, we can simulate wind flow around proposed skyscrapers before they are built. This helps us identify dangerous wind tunnels that could knock pedestrians over, or conversely, areas of stagnant air where pollution gets trapped. By rotating a building's orientation or changing its shape in the simulation, planners can optimize natural ventilation and reduce the urban heat island effect. This shifts design from an aesthetic exercise to a physics-based performance evaluation. For disaster management, we use hydrological modeling. Unlike static 2D flood maps, the digital twin lets us run dynamic scenarios. We can simulate a 100-year storm and see exactly which subway stations, hospitals, or basement apartments are at risk. More importantly, it allows for optioneering. We can virtually install a retention basin or change the pavement to a permeable material in the model, and then rerun the simulation to see if it fixes the flooding. This allows us to prove the effectiveness of our resilience strategies before spending millions on construction. It transforms the digital twin into a proactive risk management tool. Before we conclude, let's cover the golden rules or best practices for implementation. First, be purpose-driven. Don't build a twin just to have one, build it to solve a specific problem, like flooding, to keep costs down. Second, ensure data freshness. A digital twin without live data is just a dead model. Maintain the sensor connection rigorously. Third, always insist on open standards like CityGML. This prevents vendor lock-in and ensures you can still open your files 10 years from now. And finally, prioritize privacy by design. If you are using cameras or sensors, ensure citizen data is anonymized from day one to comply with regulations like GDPR. Adhering to these rules ensures your twin is sustainable and ethical. As a summary, a digital twin is a system, not just a model. It relies on the 5-dimensional architecture and the 3-layer tech stack we define today. It requires semantic standards like CityGML to make the model smart enough to answer questions. It depends on robust integration to bridge the gap between BIM and GIS. But ultimately, these are just tools. The real value lies in the applications, using simulations to shift our profession from intuition-based planning to evidence-based decision-making. As we look to the future, the integration of AI will evolve these systems into cognitive twins that not only describe the city but actively suggest planning interventions. Thank you for your attention.